the last video, we had discussed about the closed pack structure, and based on that, we had derived the relationship between the age of the unit cell and the radius of the atom. Today our discussion will be related to that only, because if the closed pack structure takes place, means if the atoms are very close to each other, the most possible proximity to each other, if they are touched, if they are occupying the most of the area of an unit cell, in that case the minimum amount of space in an unit cell will remain vacant. That we have calculated also on the last day in the form of packing fraction. So packing fraction denotes the amount of vacant space present within the unit cell. Today we are going to see, or we are going to discuss about that vacant space. These are called voids. So today our topic is voids. To understand a void, we have to revisit the closed pack structures once again. So we are going to start with one-dimensional case. So one-dimensional means the atoms, suppose the spherical atoms, which I can draw only in one dimension now because we are considering one dimension, are in contact with each other like this. Here you see, suppose I am talking about any atom. Suppose I am talking about this atom, this one. Suppose this one I am talking about. Here you see, having the minimum space between them because they are already attached, this atom is connected with this one and this one. So here, the number of atoms with which this particular atom, which is under consideration, is attached with is known as the coordination number, Cn. So in this case, for closed pack structure in one dimension, the coordination number is 2. Similar things can be drawn in case of two-dimensional case also. So in case of two dimension, I'll just make it 2D. What are the differences? So I'm just erasing it here only. Arrangements will be slightly different. Here you see, this is one arrangement. This is one arrangement. So they're connecting with each other. Let us draw one more layer. Without explaining much of it, let us draw. This is one type of arrangement, as I have said. There is another arrangement possible. That is, with black I am drawing. Carefully see the difference between the two. You should figure it out by yourself by pausing the video. Suppose here, now the second layer, here you see all the layers are attached only on this part, but at the depression, if the another layer is kept here, similarly the next layer will also be drawn at the depression. Of the previous layer. Here you see, last one also. Let me draw. This is the second arrangement. Can you figure out the difference between the two? Pause the video here and figure it out. In the first arrangement, if we take any atom, say for this one, under consideration. So in 2 dimension, if we figure out that how many atoms are directly in contact with this, it will be 1, 2, 3 and 4, right? Now if I connect, so 1, 2, 3, 4, I hope it is clear. If I connect those centers, it gives rise to a square. So this is called SCP, or we can call square close packing. Similarly, in the arrangement 2, if you choose anyone, suppose I choose this one. Now if I figure out how many atoms are surrounding it, directly in contact with this, it will be 1, 2, 3, 4, 5, 6. I hope it is clear. So in this case, I have forgotten to mention the coordination number should be 4, and in this case the coordination number is 6 because 6 atoms are attached. Now if I connect the center of these atoms assumed to be spheres, in this case circle of course because it is 2 dimension, it appears to be what? It is hexagon. So it is called HCP, or hexagonal close packing. One more thing interestingly, you can see here all the layers are same. It is A, and it is A. All the layers are of same type. So it is called AAA type. Here if you see, this layer is same with this layer, whereas this layer is definitely just the other type. So this type of arrangement is called AB type. Remember, we are till now talking only about 2D, but the actual structure we should consider in 3D. But we need to have the idea of 2D, then only we can talk about 3D.
So whatever we have seen, the same can be observed in this video as well. So here it is mentioned that the 3-dimensional modes of packing can be done in 3 steps: 1-dimensional, 2-dimensional and 3-dimensional. So of course, as we have drawn, in case of 1-dimensional, we will arrange the spheres. In case of 1-dimensional, see here, as you see, they are arranged in 1 dimension only. They are closely packed. See, the green one are the attached atoms with the selected atom over there. So the coordination number is 2. It is clearly marked which are the attached atom. In the same way, the 2-dimensional packing can also be observed. So here we are stacking rows of 1-dimensionally closed packed spheres only, one above other. There is nothing different over here. So we have shown one is square closed packing and one is hexagonal closed packing. We have drawn that on the board. Here you see with the help of the animation. So this is square closed packing. Here there is one line of atoms, there is another group of atoms are coming, and this is exactly attached in the same manner. And see another one also. This one gives rise to square close packing, because the yellow atom which is under consideration, see the green atoms are attached, there is 4 coordination number. The 4 atoms are attached with it. We have drawn the same in the board also. It's called the AA type of arrangement because all the layers are same, there is hardly any difference between them. Now let us see the hexagonal close packing. In hexagonal close packing, only the difference is the next layer will be attached in the depression point of the first layer of the spheres. So they are kept on the depression of the first layer. So if the first layer is A, the second layer has got to be the other one, which is B. Here it is clearly mentioned. Now the third layer will be the similar to the first layer. It will also be attached on the depression point of the second layer, that is B. Now if we consider this blue atom, see there are 6 atoms we have stated earlier. Here also you can see the coordination number will be 6. So there are 2 different type of layers which are kept. So it is called ABAB type, because if we keep another layer above A, it has to be B in order to maintain the same pattern. Now if we compare the square close packing with the hexagonal close packing, we will observe that the empty spaces are less in hexagonal close packing as compared to the SCP, which is the square close packing. You can see here. So if the empty spaces are less, so the packing efficiency will be higher. So the packing efficiency has got a direct relationship with the voids. These vacant spaces are called the voids. Voids are responsible for decreasing the packing efficiency. Higher will be the packing efficiency, lesser will be the voids. Now the interesting one, which is obviously difficult to draw in the board. So we are introducing the animation with the help of the 3-dimensional close packing. Here you see the first layer has been taken. This is the second layer just above it. So it is called square close packed structure. Now see carefully. Another layer has been kept and another. So the layers after layers have been kept in the same manner, but if we choose any atom out of that, you will find there are 6 atoms coordinated with one of it. In this manner only. So the coordination number is 6, and this is how they look like. See this one in the original structure. So this is called AAA type because all the layers are same, but the coordination number will be 6. So they will form a simple cubic lattice in this way. Here it is written also. So it forms a simple cubic lattice, and it is the primitive cubic unit cell, as we know. Now in case of HCP, what happens? Let us see. In case of HCP, if the first layer is kept as it is, then the second layer will come at the depression point of the first layer, and the third one will come at the depression point of the second. So that is how they are arranged. So how will we place the second layer over the first layer? Here let us see in the animation. So these are the triangular voids which is roughly visible. So the new layers will come, will cover these voids, and it will be on the position of those voids only that the second layers are kept. See now, this is the second layer, which is B. But have we covered all the voids? Answer is no. We could not cover all the voids if we see from the top. So what are the voids? There are basically two types of voids, tetrahedral and octahedral. Here they have mentioned tetrahedron, which is same as tetrahedral. Now tetrahedral will look like this. See this. So there are three atoms above which another atom is placed, and in between this kind of voids will be observed. I will be showing it on board that how it is actually formed. So you can see the voids over here in this 3D diagram. So three atoms will be in one plane and there will be another atom on top of it, and that is how the tetrahedral voids will be formed. And similarly we can see the octahedral void also. See here, there are four atoms on one layer and one atom above and one atom below. So this is how the octahedral voids are formed. See the octahedron. Here you see on there is a square planar structure where the four atoms are there, and there is one atom above and one below. So in case we need to calculate the number of tetrahedral and octahedral voids in a crystal structure, there is a simple formula. If there are n number of atoms in a unit cell, then there will be 2n number of tetrahedral voids and n number of octahedral voids. That is what it is written. Octahedral voids will be n and the tetrahedral voids will be just the double of that, which is 2n. Later on we can prove that also, and we will prove it. Now this 3D arrangement can be shown in a much more elaborated manner if we have to place the third layer over the second layer. Till now we have seen only up to 2 layers. So in placing the third layer, there can be two type of arrangements. One is by covering the tetrahedral voids, another is the covering of octahedral voids. Let us see. So first we will see the case of using third layer covering the tetrahedral voids. So these are the tetrahedral voids already generated by 2 layers. Now the third layer is coming, which is covering these tetrahedral voids. See how it looks like. It is similar to the first layer actually. In order to cover the tetrahedral voids, it will be similar layer to the first layer. So first one was A, second one was B, third one is again A. This type of structures are difficult to draw in blackboards. Only through imagination and the visualization can be the best way of understanding this. So this is called the ABAB pattern, where we are covering the tetrahedral voids. This is for concept generation only. Now you can see on this type of voids, each sphere will be in contact with 12 other, because you see here the central atom is covered with the 6 atoms below, 6 atoms on the plane, 3 below and 3 above. So the total coordination number is 12. Now there is another way, is by covering the octahedral voids. So these are the octahedral voids after the 2 layers. Now if the octahedral voids are covered, you see this arrangement, whether the third layer will be the first type or second type. If you carefully notice its position, see it is got no similarity with the first layer, neither with the second layer. So it is a completely different type of layer when we are covering the octahedral voids. So this is a C layer, it is completely new. So this is ABC type till now. So if we try to place the fourth layer above it, then we will see placing the third layer over the second layer, then we are placing the fourth layer. So this is again as similar to the first layer when we are covering the octahedral voids. So this is called ABC pattern. You will always rewind the video to see it again and again in order to visualize, because on one time it is not very easy to understand. Remember, here we are covering the octahedral voids where consecutive 3 layers are absolutely different. See what will be the coordination number. If we consider the atom, any atom which is absolutely present at the center, the atom which is not marked is the atom under consideration. So here also the coordination number is 12.
Seen from the video, animated video, that is how the atomic layers are placed in 3-dimensional way and how the voids are being generated. And it is clearly mentioned over there that there are 2 types of voids. One is tetrahedral and one is octahedral. How it is generated, that also I have explained in the video. But video is one thing, to be able to write it down or to draw it in pen and paper is completely different. So we must understand how we can locate, how can we locate the tetrahedral and octahedral voids in a 3D diagram. Obviously the movement of the particles of the atoms cannot be shown, but we will try to locate it in the simplest possible way that it be, so that we understand how the voids are actually looks like. So for that, what we will do is, in tetrahedral voids, let us talk about tetrahedral voids. TV I have written. I have chosen two atoms side by side like this. So there are 3 atoms in one layer like this. Suppose this one. So there are 3 atoms in one layer. Suppose these are the centers. And in this position, suppose another atom I am just placing from above it. Suppose I am placing this atom into this region, okay? So I have kept a gap for you to understand actually how the voids are situated. So I hope it is clear. This is going to be kept over this in this region. Now these are the centers, as I have said, and this is the center. So when these are kept together, when there is a minimum space between them, then also there will be a vacant space, a voids will be generated. Let us see what kind of void. If I join them, if I join the points, there is already a triangle formed here, and if I join this point with the rest of them, you will find something like this. See the vacant space here. If an atom is placed here, it will be connected to 4. If an atom is placed here like this, in this vacant space, it will be connected to 1, 2, 3, 4 atoms. So for tetrahedral voids, the coordination number is actually 4 because it is connected to 4 atoms. Secondly, I hope you have all imagined the tetrahedron that is being generated. This one is a tetrahedral void, and at the same time, it is also quite easy to understand that if there was another atom on this side, another tetrahedron void can be generated. So the main thing is, this is how the tetrahedral void will look like. The triangle will be formed between these three and there will be another atom, and that is how it is. Coordination number is 4. Now, along with tetrahedral void, let us see how the octahedral voids will look like. Let's see. In case of octahedral voids, the basic idea of forming the octahedral void is there will be 2 layers. First layer will be like this, as it is. Now, there will be another 3 atoms here, just the above layer. We are not actually these layers are touched with each other, in touch with each other. But I have kept some separation so that we can show the in-between space. But here, see the difference. One atom is here. Another will be here. Like this. And another will be here. I hope you have understood the difference between the two. Here, the 2 atoms are towards us and one is behind. So if I join their centers, if I join the centers, it will form a triangle. Here also, this atom is towards us and 2 atoms are behind us. Just make it a little bit bigger. Anyway, if I join this, so it has also formed another triangle, but the apex of both the triangles are just on opposite side. This is the essence of formation of octahedral voids. So the basic condition of formation of octahedral voids, that there can be 2 layers touching with each others, but the triangles that the 3 atoms over and 3 atoms below will form, their apex will be just on opposite side. Now let us reconnect. If I connect this one, let us connect the centers. Okay. And here also, this one. Try to imagine carefully. What have I done? See the vacant space between them. If an atom is placed here, then it will be in contact with 1, 2, 3, 4, 5, 6 atoms. So first thing first, coordination number will be 6. That's for sure. Whatever the vacant space that is being generated or that will be generated, if these 2 layers will come in contact with each other that I have drawn here, in that vacant space, if an atom is situated, it will be in connection with 1, 2, 3, 4, 5, 6 atoms. So the coordination number is 6. And how the vacant space will look like, this space which I have drawn with the red ink. See these two corners, this 1, 2, 3, 4 corners, isn't it like this? This much. And the point above and the point below, and these are connected actually. So it basically forms an octahedral void. So tetrahedral and octahedral side by side, I have drawn how to locate it. Now let us see what will be the number of tetrahedral and octahedral voids. There is a formula that if there are n number of atoms in an unit cell, there will be n number of octahedral voids and 2n number of tetrahedral voids. This is the formula of tetrahedral voids and octahedral voids. We can actually categorically prove that it is the case. Now here comes the most crucial part. Till now we have learnt about how the voids will look like. We have seen tetrahedral voids, we have seen octahedral voids, we have seen how the layers are connected, how the voids will be located, and what will be their coordination number. But in a unit cell, let us try to locate the individual voids, that is tetrahedral and octahedral. So actual locating the voids will be drawn right now. So since I will be starting with tetrahedral voids, so let us draw the tetrahedral voids here. In order to do that, I have kept it as it is so that you can visualize. Now there are numerous videos where you can see how it is formed. But as I have said, if you can draw it over here, that means you know it properly. So see, we will be drawing it in FCC because in FCC it is much more clear. So first thing first, I have to draw a cube. A cube has been drawn. This is a joint. Now, since it is an FCC atom, I will only be drawing those atoms, although there are atoms present at the corners, present at the center of each faces that we know, but I will be drawing only those atoms which are required. So, I have chosen to draw the atoms on the center of this face. I hope you can realize. Center of this face, this one above this side, and the face which is present at the back, that means this one. So 3 atoms I have drawn. And with the similar therapy, if I join their centers, I'm trying to make it clear. If I join their centers, they will form a triangle like this, similar to that. These 3 are actually connected, close packed structure, but I cannot draw it like that, it will become very clumsy. So I have drawn it like this. Now, the 4th atom, which should be above this layer, is this corner atom present here. Now, can't you see the similarity between the two structures? Here, our job will be to connect them. this one. So this is the first tetrahedral void. The spaces in between is nothing but a tetrahedral void. Similarly, on the other side, here also, I have taken this face center atom, I have taken this face center atom, and the face which is towards us, at the center of that I have taken this atom. Okay, these three are chosen, and these corner atoms are taken. So obviously the center of these three will form a triangle, and if I connect each of these, it will be like that. See, I have drawn two tetrahedral voids. I hope you have understood the presence of the voids here. Right? Now, if I want to see what will be the center of the void, the void which is present here, if an atom is placed, what will be the center of that atom? Let us draw. I am using this green color. So it will be here, I think. And on the other side also, it will be here. These two green points. Check carefully. These two are the center of those atoms which is present at the void. Means an atom, if it is placed on the void, the center of that I am determining with the help of this green point. If I join these two points, if I join these two, from here to here, if I forcefully join, so on that line there are two center of the void which is located. That means on this line itself two voids are located. What is this line? Can you see any speciality of this line? Yes, it is nothing but body diagonal. That means we have proved that in the body diagonal of an FCC lattice there are two tetrahedral voids located. Now you tell me, in an FCC atom or in any unit cell, any cubic lattice, in a cubic lattice how many body diagonals are present? There are 8 corners, so there will be like 1, 2, 3, 4 body diagonals. So there are 4 body diagonals, and since there are 4 body diagonals, each body diagonal will have 2 tetrahedral voids. So there are 4 into 2, 8 tetrahedral voids. And now in this FCC lattice, normally how many atoms are there? So FCC consists of 4 atoms. So if there are 4 atoms, there are 8 tetrahedral voids. This again proved that if there are n number of atoms in an unit cell, there will be 2n number of tetrahedral voids. So a cubic unit cell, 4 body diagonal, in each body diagonal 2 center of the tetrahedral voids will lie. That means the total tetrahedral voids will lie. So there are 2 tetrahedral voids in each body diagonal, 4 body diagonal, that means 8 tetrahedral voids. In an FCC there are 4 atoms, so there will be, if n number of atoms are there, there are 2n number of tetrahedral voids. Same thing can be proved in case of octahedral voids also. The next one that we are going to attempt is to locate the octahedral voids. So already I have drawn a miniature of that, we have shown it already. Just concentrate on these red lines. What is that basically? See, if I take the atoms like this, these atoms 1, 2, 3 and 4. So they will form a square planar structure like that. One atom will be above, that means one atom will be here and one atom will be below, that means just behind of it, isn't it? So in order to draw this red line separately, we have understood that 1, 2, 3, 4, these will form the square planar structure like that. There will be 4 atoms onto these corners. There will be one atom here and one atom below. So like this, if I join them, they forms the square planar structure. Now, how to locate that? So this is a octahedral void. How to locate that in the cubic unit cell of a BCC lattice? Let us do this. So let us draw a cube. Okay. Now corners have been joined. Cube is ready. Again, like the previous case, I will only include those atoms which are necessary. So here you have seen that this is how the octahedral structure will look like. That means 4 corners, 1, 2, 3, 4 corners will be occupied by 4 atoms. So first, let me choose those 4 corners. So the atoms are this one, then on this side there is another face, right? At the center of that face there will be another atom, and the center of this face also there is another atom. So these 4 I have chosen. 1, 2, 3, 4, these are the 4. So I'm joining them. Okay. Now, one atom above, one atom below. The below, this face center atom can be easily taken. And for above, you see, above this unit cell, there will be another unit cell which is attached. So for that, there is a face, because one unit cell above another unit cell, that is how the cubic lattices are packed. So this face will also have a center over here in this region, a little bit above. So if I join those, it will look like this. See now. So and isn't it same as this one? So it is an octahedral void which I have tried to draw. The center of this octahedral void will be in this region. This is the void. So the center lies here. If it is spherical, see, it is present on the center of an edge also. So the octahedral void, the center of octahedral void is located at edge, at the center of the edges. There will be another type of octahedral void. To see that, see here, one face will be this face towards us, one will be this one, this face center, one is this one is the face which is behind us, one is the face which is towards us. These are the 6 atoms. Again, this is the face center, this is another face center, this is already taken, these two. This is the face which is behind, this is the face which is towards us. Now if I join this with the help of this green line, see, first this is the square planar one, this is the base, one above which is here, one below which is here. So let us join this. Should have been dotted line because it is behind. Similarly, here also let us join. So here it is clearly shown that there are two different type of octahedral voids can be generated within a face center. Remember, this is not the only octahedral void. It can be drawn here, 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 in many positions. So there are two types of octahedral voids. One is, I have forgotten to mention that, like we have found out the center. This is what? Center of octahedral void. Similarly, there will be another center here of octahedral void. So there are two centers of octahedral void at two different positions. So now, from this diagram, we have found out two types of octahedral voids. Two types. One is whose center is located at edge center. This one is what? The body center. At body center. So there are two types of octahedral voids in a FCC unit cell. One is at edge center, one is at body center. Now the edge center atom will be shared by how many? How many lattices? How many cubes? 1, 2, 3 and 4. This one will be shared by 4 cubic lattices. So this volume of it will be shared by 4. So there are how many edge center? There are 1, 2, 3, 4 like that. There are 12 edges. So there are 12 edge centers, and individually each one of them will contribute 1/4 of it. So there are 3 number will be 3. And at body center, there is only one body center. So, and it is fully within, there is no part of it which is outside. So 1 into 1. So there are how many atoms? In total 4. So there are 4 octahedral voids. We have chosen FCC atom. So how many atoms? There are 4 atoms for FCC and there are 4 octahedral voids also for FCC. So here also it is proved that if the number of atoms is n number of atoms, n number of voids. So if the number of atoms is n, there will be n number of octahedral voids which is formed, but in case of tetrahedral, as you have seen, it is twice of that. So this is how the voids are located, calculated, and remember the center of the void has to be determined, and accordingly their contribution within how much is actually present within a particular FCC unit cell, that is to be calculated.